today I want to talk a little bit about hydrolysis and how the pH can change when you add a solute to solution. So if we're thinking about ionic compounds that dissolve in water, so water is your solvent, some ionic compound is your solute, then a lot of ionic compounds, when they dissolve, they're dissociating, right? So if they dissolve well, then you have a lot of ions in solution. They're strong electrolytes. And if they don't, if they're fairly insoluble, then they'll still probably dissolve a little, but not as much. So it's kind of a weaker electrolyte. And this is going to have an impact on the pH. And remember that hydrolysis is the splitting apart of water. And it's the splitting apart of the water molecule that causes that change in pH values here. So a couple things concept-wise first before we get into some sample problems is that ions in solution can change the pH. We already know this, and you've probably seen this in any experience that you've had with the ocean, right? We know that the ocean is salty. It has a number of different ions in it. It has sodium, it has chlorine, it has calcium, it has bicarbonate, it has all sorts of interesting ions in it. That salt content makes it slightly on the basic side of things. So the pH of the ocean is around 8.1. It's in the 8 kind of range, depending on where you're at. And so this slightly basic nature is because of the fact that there's these dissolved ions in there. So why does this happen? Well, it happens because the anions from weak acids make solutions basic, and the cations from weak bases make the solutions acidic. So that's probably already frustrating because we have something that's coming from an acid, meaning that I dissolve the acid and it makes the solution slightly basic, right? So that's a little bit annoying, but we'll kind of talk about that in a little more detail. So the reason that this happens is because they hydrolyze the water. Remember, our H2O is so unique and interesting because it's non-metals that are covalently bonded together, but we know that water can auto-ionize, meaning that it can separate into its component pieces, which its component pieces are ions, which is wacky, right? It's just kind of a weird, interesting thing about water. Water is so interesting and unique. And so because it can do this, then that allows for it to have some interesting potential behavior when it's mixing with other things. And the things that will do this to water are things that disrupt the water from wanting to be together. Because if I have a hydrogen and a hydroxide in solution, they're going to want to form water. But if you throw something else in there that disrupts that process, that disrupts the equilibrium, and we kind of talked about that with Le Chatelier's principle too, and we'll bring that back, then that's going to mess with something like the pH, right? It has chemical implications. So let's think about this in terms of sodium chloride, because that's one that we're all pretty familiar with. So our table salt here, if I have solid sodium chloride and I dissolve it in water, so I'm putting water as kind of a reaction condition here, then it dissociates into its component pieces. We know that all the group 1 metal cations, so all of our alkali metals, are always soluble all the time. So this is a pretty soluble compound. We've experienced that in our day-to-day life. So now the real question is, when these ions are in solution, what are they going to do to the water, if anything? So if I have the sodium ion and I react it with water, and again thinking, is this going to be a chemical reaction? Am I going to have this rearrangement of chemical bonds that is potentially possible with water? So now we're thinking, well, water is basically hydrogen hydroxide. So which of the parts of that water would sodium be the most interested in? Well, as a cation, it's going to be most interested in the hydroxide. So the real question is there going to be a reaction? Is there going to be a rearrangement of chemical bonds? And if it did, it would be in the formation of sodium hydroxide. Would that form? That's the question mark there. And the answer is no, it would not form, because this is a strong base. And we know that sodium hydroxide is a strong base. It's also called lye or caustic soda. So this is not something that's going to form, because strong bases dissociate completely in water. So this would just split apart in water. The water itself is not going to be hydrolyzed. The hydroxide would rather be part of the water than it would be as part of this compound. So there's no hydrolysis here. If I have a cation that comes from a strong base, then there's no hydrolysis. Now let's look at our chloride ion. What is it going to do to the water, if anything? Again, we're thinking about water as hydrogen hydroxide. Now, chloride is a negative ion, and an anion is going to be mostly interested in the hydrogen. So if we're thinking what forms or what could form if this chloride was going to come in here and mess with this water. Well, if it messes with the water, then it would pull that hydrogen away, forming HCl, hydrogen chloride. But one of the things that we know about hydrogen chloride is that it's a strong acid. Right? If we're naming it as an acid, if we're naming it in solution, it's hydrochloric acid, which is the primary component of our stomach acid, for example. And we know that it's a strong acid because of the Ka value, or we might know it's a strong acid because our chemistry professor has made us memorize all of the strong acids, or our biology professor has made us memorize all the strong acids. If so, kudos to them. So we know that HCl is a strong acid, and therefore there is no hydrolysis. It likes to separate in water. It's not going to pull that hydrogen away from the water. It wants to be separated. Once that hydrogen is back into solution, it would be water again. That's the drive. Okay, hopefully so far so good. Let's look at another couple examples here. What happens when I dissolve ionic compounds in water? That's kind of where we're going here. Okay, so let's take zinc chloride and dissolve it in water. Most chlorides are pretty soluble, so we'd end up with zinc ions and chloride ions. So the first thing we need to do is figure out, would zinc 2+ do anything to water? Is it going to hydrolyze my water? So if we're thinking, well, what would form? If we think about water again as hydrogen hydroxide, a positive ion, a cation like this, is going to be most interested in the hydroxide. So what I'm really asking is, would zinc hydroxide form? And if it would form, then that's going to have implications on my water. So I need to say, well, would zinc hydroxide form? Is it a strong or a weak base? And this isn't one of my strong bases. My rule for my strong bases is group 1 or 2, so the alkali metals or the alkaline earth metals paired with a hydroxide. Those are all strong bases, except for beryllium, besides beryllium. So this is a weak base. We know that weak bases like to form, right? If we're thinking about a Kb value for this, it's quite low. So this thing would really like to form. It's going to form some of this. And if I take some hydroxides from my water, then that's going to leave me some hydrogens left over. Now we're going to have to do some balancing here. It looks like I've used up 2 hydroxides, so I'll probably need 2 of these guys, which means that I probably had 2 of these if we're thinking about balancing our overall process. But the take-home message here is that if I have hydrogen ions in solutions, that's going to make the solution acidic. So I dissolve the zinc chloride, and I get a slightly acidic solution. And we've already looked at chloride, so we know that chloride is not going to have an impact on my overall process, right? Because it comes from that hydrochloric acid. So we'd have a slightly acidic solution once this thing forms. It's a weak base. It would actually be a precipitate. All right, let's look at another example. Let's take potassium carbonate. When I put potassium carbonate in water, then I'll end up with potassium ions and carbonate ions. So I need to take my potassium first. I'll just do one of them. So the question is, what is this guy going to take from water? Well, as we've seen with the other examples, a cation is going to take the hydroxide. So the question is, would potassium hydroxide form? And hopefully now you're thinking to yourself, well, what I need to know about potassium hydroxide is if it's a strong or a weak base. And what I know is that it's a strong base. because I know my patterns based on the periodic table. And so if it's strong base, there's no hydrolysis. Let's look at the carbonate. When I put carbonate in water, then the carbonate is a negative ion. It's an anion, so it's going to want to take the hydrogen. So we'd have this guy if we took the hydrogen. So this is called the bicarbonate ion, or the hydrogen carbonate ion. And what we know about bicarbonate is that it's a weak acid, slightly weakly acidic. Okay, so HCO3, or if we were to take a couple of these protons away, this would be H2CO3, which is carbonic acid. So these two have the ability to donate a hydrogen, which makes them slightly on the acidic side. It's weak. And because it's weak, it will want to form, right? That's what that weakness is. It wants to stick together. And if this pulls a hydrogen away from that water, then what's left over is a hydroxide. If I have hydroxide in solution, that makes it basic. Now, if I have one thing that gives a solution that's slightly acidic, so it comes from a weak base, and something that gives it slightly basic, meaning that it comes from a weak acid, then it would really be about the concentrations at that point, which concentration is going to have more of an impact. And if it's kind of a 2-to-1, like in this case, then the potassium would have more of an impact than the carbonate, etc. And we can get into the details of that and do some math on that to figure out what the pH would be of the overall solution. So we can do some icebox equations to figure out what the actual pH value would be. But this is just kind of it in a conceptual nutshell. And we'll do some more practice with this with some actual numbers.